There is a stretch of mountain railroad in the American West where, on a cold night, you can watch a freight train glow. Not the headlight, not the red markers on the last car. The roof. Just behind the cab of each locomotive, through a set of louvered panels, something is burning a dull orange. It is the exact color of a stove element, stretched out into a rectangle roughly the size of a doorway. A fan above it is howling loud enough to bury the sound of the diesel engine underneath. And that engine, if you listen for it, is barely working at all. It is idling. Behind those locomotives, 15,000 tons of loaded freight is coming down a 2% grade. The machine that would normally be roaring at full throttle is sitting there at idle, running what amounts to an enormous electric heater on its own roof. That heater is what is holding the train. None of this is a malfunction. It was designed, tested, specified on purchase orders, and paid for. An industry that measures fuel by the trainload, that will spend a decade chasing a 1% efficiency gain, decided a long time ago that the correct way to bring a heavy train down a mountain was to generate several thousand horsepower of electricity it had absolutely no use for and then destroy it on purpose, in the open air, above a mountain where it warms nothing at all. So why would anyone build that? The answer starts with a shift in how you think about brakes. A brake does not make energy disappear. Nothing makes energy disappear. A brake is a disposal system, and every real question in railroad braking comes down to the same two. Where are you going to put the energy, and how fast can you get rid of it? Let's do the accounting. Take a loaded train, 10,000 tons, standing still at the top of a mountain pass. It has no kinetic energy whatsoever. What it has is height, and height is a fully charged battery that nobody can switch off. 20 miles of 2% grade will drop that train a little over 2,000 feet. Run the arithmetic on the mass and the drop, and you get a figure somewhere in the neighborhood of 15,000 kilowatt hours. That is more electricity than an average American house uses in a year, arriving over about 45 minutes. Averaged across the descent, the train has to shed roughly 20 megawatts continuously, the whole way down. That is a small power station's worth of output, and the train's entire job is to throw it away as fast as it shows up. And you do not need a mountain for the numbers to get uncomfortable. One engineering study lays it out plainly. A 5,000-ton train slowing from 30 miles an hour to 25, a nudge barely noticeable in the cab, has to dump about 35 kilowatt hours somewhere. Somewhere. That word is carrying the entire history of railroad braking. The energy is not optional, and it is not negotiable. Physics lets you choose the address, and nothing else. For the first century of railroading, there was one address. You put it in the wheels. Rub two pieces of steel together hard enough, and motion becomes heat. That is the whole idea, and it works beautifully in small doses. The trouble is the phrase, small doses. A wheel can only absorb so much heat before it stops behaving like a wheel. On steam locomotives, the problem was structural. The tire, which is the replaceable steel ring that forms the running surface, was heated in a ring of gas jets until it expanded, dropped over the wheel center, and then allowed to cool until it clamped down with a grip you could not break with a hammer. Overheated in service, and you were simply running the factory process in reverse. Crews were taught to use the engine brake in short applications, lightly, and to be nervous about it, for exactly that reason. Freight cars failed differently. Push enough heat into a brake shoe and the friction material itself softens and goes slick. The harder you brake, the less braking you get. That is the worst possible property a machine can have on the side of a mountain. And it has a name that sounds far too gentle for what it does. Fade. Then there was the air itself. The compressed air brake, in its classic freight form, is a one-way conversation on a long grade. To apply the brakes, you reduce pressure in the pipe running the length of the train. To get that pressure back, you have to release and let the pumps refill the reservoirs on every car. Cycle that too many times on a descent, and you can arrive at the bottom of your air supply while still near the top of the hill. It is not a mechanical failure. It is an arithmetic failure, and it has killed people. So railroads solved it the way they solved most things in the 19th century, with labor. A train would stop dead at the summit of a grade, and brakemen would walk the length of it, car by car, turning small valves by hand. These were retainers. Their job was to trap a modest amount of pressure in each brake cylinder on the order of 20 pounds per square inch, so the car held a light, steady drag even while the engineer released everything else and recharged the system. Then the train crawled down, and at the bottom, somebody walked the whole train again to turn every one of those valves back. Picture that in January. Picture it at night, on a running board, on a car that is already smoking. Because they did smoke. Old hands describe the smell of a heavy descent before they describe anything else. Hot iron, scorched shoes, a haze hanging under the cars. And at night, if you stood beside the track, you could see faint red rings on the wheels of a train coming down a grade, which is worth sitting with for a second. Those glowing wheel rims and the glowing roof panels we started with are the same event. Identical energy, identical physics, identical color temperature. The only thing that changed in 100 years is the address. And the address mattered enormously because there is a deeper problem with heating the wheels. The wheel is also the component keeping the train on the rails. You are asking one piece of steel to do the braking, the guiding, and the load-bearing all at once, and you are cooking it while it works. Somebody was always going to try to build a brake that never touched the wheel at all. What is surprising is how early they tried. In the 1860s, a French engineer named Louis Le Chatelier worked out something that sounds like nonsense until you follow it through. A steam locomotive's cylinders push the wheels around. But if you reverse the valve gear while the locomotive is still rolling forward, the arrangement flips. The wheels now push the pistons and the cylinders become air compressors. The engine starts fighting the train. There was one enormous problem. Compressing air heats it ferociously, and a cylinder full of scalding gas with no lubrication will destroy itself in minutes. So Le Chatelier fed a controlled stream of hot water from the boiler into the cylinders. The water flashed to wet steam, and that steam did two things at once. It cushioned the stroke, and it carried the heat away up the stack. Read that again, because it is the whole story in miniature. He built a brake that turned motion into heat, and then he had to invent a way to get the heat off the machine before the machine died of it. It half worked. The system caught on in France and later on mountain lines across Central Europe and Russia. In Britain, it mostly failed, and the engineers of the day blamed the crews rather than the design. In Austria, railways saw a run of broken connecting rods and cracked cranks when drivers let too much water into the cylinders and effectively tried to compress a liquid. The margin between working brake and ruined locomotive was a driver's judgment on a dark hillside. A few years later, on a Swiss rack railway, another engineer took the same principle and used air instead of water, with valves in the exhaust to control the resistance. That version was safer and variants of it spread. But every one of these systems ran into the same ceiling. The energy of a descending train is measured in megawatts, and a steam locomotive is a poor place to put megawatts you do not want. The heat had nowhere good to go, so it went into the cylinders, the rods, the bearings, the parts you cannot afford to lose. What was needed was something that could absorb an enormous amount of power and simply not care. And by the time that thing arrived, it was already sitting on the train, doing another job entirely. Here is the fact about a diesel locomotive that trips almost everyone up. The diesel engine is not connected to the wheels. There is no gearbox, no clutch, no drive shaft running down the frame. The engine turns a generator, the generator makes electricity, and the electricity turns a motor on every axle. What is rolling past you at a crossing is an electric locomotive that happens to be carrying its own power station, which means every one of those locomotives is hauling around 6 electric machines. And an electric machine has a property that borders on unfair. It runs both ways. Feed current into a motor and it makes torque. Turn that same motor from the outside and it makes current. It is not a different device in the second case. It is the same copper and iron doing the same thing with the arrows reversed. So when an engineer wants to slow a train, the locomotive disconnects its traction motors from the main generator and reconnects them as generators, driven by the axles. The wheels are turned by the train. The train is pulled by gravity. And gravity, whether it likes it or not, is now in the electricity business. Where does the braking force come from? Generating current is not free. The instant a generator has somewhere to send its output, it becomes hard to turn, and that resistance runs back through the gears into the axle and down to the rail. That is the brake. The more current you draw, the harder the whole train has to fight to keep moving, which means an engineer easing a lever back in the cab is not squeezing anything against a wheel. He is deciding how much electricity 15,000 tons of freight is going to be forced to manufacture on the way down the hill. And that leaves the question the entire system is built around. Where does the current go? On a diesel locomotive, there is no good answer. There is no wire overhead. The diesel engine cannot absorb electricity. It produces it. The batteries on board exist to crank the engine and would take a rounding error of what is arriving. Several megawatts are showing up continuously with nowhere to be. So the industry built a place for it to die. The dynamic brake grid is one of the least sophisticated objects on a modern locomotive, and that is exactly the point. It is a frame holding thin metal ribbons, folded back and forth like an accordion and wired in series. Functionally, it is a toaster element the size of a filing cabinet, and there are several stacked behind the cab under those roof panels. Current is forced through, the metal resists, and resistance is heat. A typical grid installation is rated to swallow something in the range of 4,000 to 5,000 horsepower, which is why the fan matters more than the grid does. Without forced air, those ribbons would cook themselves in under a minute, so a large blower drags outside air through the stack and throws the heat out the roof. And the elegant part is how the blower is powered. On many locomotives, it is driven by the braking current itself, wired into the same circuit as the grids. Brake harder, more current flows, and the fan spins faster. The cooling scales itself to the load automatically, with no sensor, no controller, and no software involved. It cannot be forgotten, and it cannot be overridden. It is the rare safety system that is impossible to switch off, because it is made of the same electricity it is protecting you from. That fan is why crews can hear a train in dynamic braking from a long way off, and why the sound is so disorienting the first time. The prime mover is at idle. The scream over the top of everything is a cooling fan working for a living. Step back and look at what has actually been achieved here, because it is not what people assume. The heat pouring off that roof is precisely the heat that used to go into brake shoes and wheels. Nothing has been saved. Not one joule. It has been moved. Off the friction surfaces, off the components that keep the train on the rail, and into a lump of steel in the roof whose entire purpose in life is to get incandescent and not care. That is the invention, not efficiency. Relocation. And if you go hunting for where the idea came from, you find something that makes all that wasted heat look almost embarrassing. Because the original version threw nothing away. Electric railways got there first, and they got there better. An electric locomotive does not carry a power plant. It carries a connection. And a wire, unlike a diesel engine, is perfectly happy to work in both directions. When the motors on an electric locomotive flip into generator mode on a downgrade, that power can be pushed back up through the pantograph into the overhead line, where any other train drawing power on the same section can simply drink it. Between 1915 and 1917, an American railroad strung wire over more than 400 miles of Montana and Idaho mountains and did exactly that. Loaded trains coming down the passes fed current back into the catenary. Trains climbing the same grades used it. The mountains were, functionally, wired together. A description of the operation from that era gets at what it meant on the ground better than any diagram. A heavy train could be eased all the way down a mountain without a single hot brake shoe anywhere in the consist. Even then, the destination could evaporate. If no train nearby happened to be pulling power at that moment, the energy still had to go somewhere, and racks of resistors near the substations burned off the surplus. Same principle, same heat, just standing beside the track instead of riding on the train. So follow the chronology and it runs backwards from what you would expect. The elegant version came first. The wasteful version came second, and it came second because it arrived with the diesel. Dynamic braking is regenerative braking with the destination deleted. Everything up to the decisive moment is identical. The motors reverse roll, the current flows, the train slows. Then the electricity reaches a fork where one path leads to another, train climbing a hill somewhere ahead, and the other leads to a metal ribbon in the roof. The diesel locomotive only ever had the second path. It brought its own power plant so it would never depend on infrastructure, and the price of that independence was that it had nowhere to send anything back. That trade, freedom from the wire in exchange for burning the energy, is the bargain North American freight railroading made. It is still running inside every locomotive on the continent. You might assume a system this useful got adopted immediately. It did not. Dynamic brakes appeared as an option on the first mainline diesel freight units of the late 1930s, and for years they stayed an option, a box checked or left blank on an order form. They were expensive. They piled a large amount of extra electrical apparatus onto a machine that had no computers to manage any of it. One estimate puts it at something like 40% more circuitry on a locomotive of that era. And the grids themselves are consumable. They degrade every time you use them. So railroads bought them geographically. Roads that crossed mountains specified dynamics on their first diesels and never looked back. Roads whose territory was flat declined them, stayed with air brakes, and pocketed the difference. For a while, the map of dynamic braking in America was just a topographic map with the level parts erased. Two things ended that. Locomotives became too valuable to strand in one region, and a fleet where half the units can only work in certain territory is a dispatcher's nightmare. And then, less predictably, dynamic braking turned out to be useful on flat ground too. for the ordinary business of speed control rather than the drama of mountain descents. Today, it is effectively standard equipment. If you are finding this worth your time, go ahead and subscribe. We cover railroad engineering and locomotive history every week, but it has limits, and every one of them traces straight back to that lump of metal under the roof. Start with speed. The faster the wheels turn, the faster the armatures spin and the more voltage they produce. Slow down, and the output collapses. Early systems made their strongest braking somewhere in the mid-20s of miles per hour and faded to nothing near walking pace, which means that at the precise moment you most want to be stopping, the last few miles an hour, the dynamic brake quits and hands the job back to the air. Then there is the thermal ceiling. On a typical design, the motor fields will tolerate close to 1,000 amps of excitation, but the current allowed into the grids is capped far lower, in the region of 700. Not because the motors cannot produce more, because the grids and their blower cannot get rid of the heat fast enough. Maximum braking effort sits exactly where those two limits cross. The brake is not constrained by electricity. It is constrained by cooling. Engineers found a clever way around the low-speed problem. If the voltage is falling, lower the resistance to match. Short out sections of the grid in stages as the train slows, and the current keeps flowing. That is extended-range dynamic braking, and it pushed useful retarding force down into single-digit speeds. It was not free. Each stage was a discrete jump, and a discrete jump in braking force at the head of a mile-long train is felt as a lurch. Slack runs in, couplers take up, and the whole consist shifts. Crews learn to anticipate those steps the way a driver learns a bad gearbox. Modern control electronics smooth the transitions, and alternating current traction units hold their braking effort almost down to a standstill. There is a subtler limit, and it has nothing to do with heat. Dynamic braking exists only on the locomotives. On a 100-car train, all of that retarding force is applied at the front across a handful of axles, while a mile of loaded freight keeps pushing from behind. The train compresses. Couplers bunch tight. Apply too much dynamic brake, too quickly, in the wrong place, and a compressed train can shove itself sideways off the rail. Operating rules restrict how much dynamic braking is permitted in certain situations, and the reason is not thermal. It is geometry. So in practice, engineers blend. The dynamic brake does the sustained work of holding speed. The air brakes get layered in when the grade demands more than the grids can absorb. Each covers the other's weakness. Setting it up has its own quiet choreography. Throttle to idle. A pause of several seconds to let residual current in the motors bleed away, because rushing that step can slam the braking on and run the slack in hard against the rear of the train. Then the lever moves over into the braking range, and the engineer feels the slack gather and bunch, car by car, all the way back into the dark, before he asks for any real retarding force. Descending a mountain in a modern freight locomotive is less like driving and more like managing a budget in two currencies, one of which can run out. On one morning in Southern California, a crew went down a mountain believing that budget was far larger than it was. Cajon Pass climbs out of the Mojave and drops toward the Los Angeles basin, and it drops hard. Early on the 12th of May, 1989, a freight train crested the top with 69 cars of trona, a dense sodium mineral, behind 6 locomotives. The paperwork the crew had been handed put the train at a little over 6,000 tons. It was closer to 9,000. That was the first error, and it was made in an office, in a clerk's arithmetic. The second error was worse because it was mechanical and invisible. Of the 6 locomotives, only 3 had working dynamic brakes. The crew at the head end did not know that the helper units at the rear were partly dead. Nobody had a mechanism for telling them. So the train started down with roughly half the electrical braking it believed it had, carrying roughly half again the tonnage it believed it was carrying. The dynamics did what they could. The air brakes were left to do everything else, which meant the friction brakes were being asked to absorb almost the entire energy of a 9,000-ton descent. They could not. When investigators went through the wreckage, they found freight car wheels that had shifted position on their axles. The steel had been heated so severely by continuous braking that the interference fit holding wheel to axle had let go. That is what a thermal overload looks like when you find it lying in a scrapyard. The train accelerated. An emergency application on a train already that hot changes remarkably little. It entered a curve in a residential neighborhood at a speed calculated afterward at around 110 miles an hour. On track posted for a small fraction of that. The conductor and the head-end brakemen were killed in the locomotives. 2 young boys were killed in a house beside the track. 7 homes on that street were destroyed outright, along with the lead locomotives and every car in the train. 13 days later, a buried petroleum pipeline that had been damaged by the cleanup equipment ruptured on the same block and burned, taking 2 more lives and 11 more houses. The safety board's conclusion was not about broken hardware, it was about information. The probable cause came down to the failure to determine and communicate the true weight of the train, the failure to communicate the condition of the dynamic brakes, and an operating rule that gave the crew inadequate direction. Investigators also found the railroad's training program contained nothing whatsoever on how to regain control of a runaway. And there was one more finding, the kind that stays with you. Had the train come over, the summit at 15 miles an hour or less, the brakes it actually had would probably have been enough to hold it. The margin existed. It was consumed by 2 pieces of information being wrong. That is the real character of dynamic braking, and it appears on no engineering diagram. The system is a budget calculated before the descent begins, in tons and grade and working axles. If the calculation is wrong, you discover it at the one point on the mountain where nothing can be done about it. Which brings us back to all that heat and to a question the industry has been circling for half a century. The energy is real, and it is enormous. Every year, thousands of trains bring vast quantities of gravitational potential down the same handful of mountain passes and convert all of it into warm air. Researchers at an American university once put a number on a single pass. If you could capture the dynamic braking energy from the freight train's descending Cajon and actually use it, you would save over 1 million gallons of diesel fuel a year. From one mountain. Nobody has ever captured all of it, but some railroads never had to throw it away in the first place. In the far north of Sweden, iron ore comes out of the ground hundreds of miles inland and has to reach the sea. The heavy direction of travel is downhill, loaded trains descending toward the Norwegian coast, and the line is electrified. So the loaded trains regenerate on the way down, feeding the wire, and the empty trains climbing back up run on that power. By published accounts of the operation, the descending trains generate several times what they themselves consume, enough to lift the empties back over the mountains with a surplus left for the public grid. Sit with what that means. On that railroad, the ore is not only cargo, it is fuel delivered by gravity, and the mountain is the tank. So why does every electrified railway not do this? Because a wire is not a battery. On direct current systems, the overhead line can only accept power if something is drawing it at that exact moment. Usually another train accelerating on the same electrical section. If nobody is, the voltage climbs, and the braking train has to dump its energy into onboard resistors anyway. Generating the power is easy. Finding a customer for it in the same second it exists is the hard part. The engineering answer is to give the energy somewhere to wait. Substations are being rebuilt with inverters that can push surplus back into the public network instead of only pulling from it. Others are getting banks of batteries, supercapacitors, or flywheels beside the track, absorbing what a braking train produces and releasing it when the next one pulls away. Some operators tune their timetables deliberately so that arrivals and departures overlap, turning a schedule into an energy management tool. The prize is substantial. Studies of electrified railways put the braking energy theoretically available at something like 40 to 45% of everything the system consumes. Measured recovery in practice has run far lower, with figures around 19% turning up in the research. The gap between those two numbers is the entire problem, and it is mostly a problem of timing and storage rather than of electricity, which leaves the American freight railroad with no wire overhead, thousands of horsepower of heat pouring off its roof, and one obvious question that took a very long time to become answerable. What if the locomotive carried the destination with it? That is the logic behind the battery locomotives now being tested in mainline freight service. One prototype, a full-sized road unit packed with tens of thousands of lithium cells, ran in commercial service between yards in California, coupled between 2 conventional diesels. It charged at the yard, and then it charged itself again on every descent along the route, taking the current that would have gone to the grids and putting it into cells instead. Across the whole consist, fuel consumption fell by roughly 11%. The follow-on design targets several times the storage capacity and considerably larger savings. The constraints are real. Braking effort is still concentrated at the head end, which limits how many braking axles you can reasonably put there. Moving energy out of the traction motors of one locomotive and into a battery riding in a different one is not a trivial piece of engineering. And a battery that fills up halfway down a long grade is functionally a resistor grid with extra steps. But the shape of the change is clear enough. For 80 years, the defining fact about braking a diesel-electric train was that the electricity had nowhere to go. That sentence is finally starting to come untrue. none of which erases the thing we started with. Somewhere tonight, on a grade in the mountains, a train is coming down with its engines at idle and its roof panels glowing dull orange, a fan screaming above them, warm air rolling off into the dark. Over country where nobody is watching, it is not an accident of old technology. It is the visible receipt for a piece of physics that nobody gets to skip. The price of bringing something enormous down a hill under control, paid in full, in the open, in real time. The grid in that roof is the most honest device on the train. It does not hide what braking actually costs. It holds it up in the cold air where you can see it. So the next time you are stopped at a crossing at night and a heavy train comes past off a grade, do not listen for the engine. Listen for the fan. That howl riding over the top of everything is the sound of 15,000 tons being converted very carefully into nothing at all but warmth.